Hello, everyone, and welcome back to my last day here for the EET423 class. And today I'm going to be covering bus protection topics, really trying to just do a high-level overview of the different methods that we use as protection engineers to protect power system buses. So today we're going to cover several topics and look at a variety of different methods for protecting buses. I'll do an introduction and talk about what buses are, kind of where they fall into the power system. We'll take a look at different bus protection schemes that we can apply, and we'll be really breaking those down into a few different varieties. First, we'll be talking about time coordinated protection. Then we'll be talking about a zone interwalk scheme where we similar to the pilot scheme we discussed in the line protection module, we have some level of communication between the devices to, um, you know, better identify the location of the fault, and that has some advantages that can be used. And finally, we'll talk about a couple of varieties of differential schemes. Differential protection is one of the more commonly used bus protection methods, and it's really very robust and meets a lot of our protection system objectives. I'll also give you some links and some references for continued reading. There's a lot of great information about all sorts of varieties of bus protection and the considerations on when you apply each. So I'll have those at the end of the slide deck for anyone who wants to dig in and learn a little bit more. All right, so buses act as a connection point between multiple system components. So typically, any substation is going to be comprised of some type of bus connecting multiple parts of a power system together. These could be transmission lines, distribution lines, transformers, capacitor banks, really any type of primary equipment we're looking to connect into the power system is going to be somehow connected up to a bus, which is going to be its connection point to other parts of the system. So obviously buses are pretty critical aspects of power system operation, and protecting them is highly critical as well. So bus faults in general are going to cause a large disturbance to the power system overall. There's a couple different station arrangements that can limit that impact, but for a straight bus configuration like what we've got shown over to the right here, if you have a fault on the bus, you're tripping all 5 of those sources off the system. So you're going to have a major impact to your system operation. If those are all feeding customers, you're going to be tripping off, a large portions of your power system based on that one type of fault. So it's very critical that our protection operates with high reliability, and in many cases, it's very critical that we're operating very fast. So in general, we're trying to apply a bus protection zone that will operate for faults on the bus, and similar to what we talked about with our line protection and other applications, we've got to cover any of the expected fault scenarios that could happen on the bus. So whether that's 3-phase faults, line-to-line faults, line-to-ground faults, different types of equipment failures, the potential for impedance in those faults. So there's a lot of things we have to consider. One of the advantages of buses is they're designed to be a connection point, so they really don't have any impedance associated with them that really impacts how we look at their fault response. So generally, you can simulate a fault on a bus, and that's going to be the fault current that you expect for that area. You don't have to look at fault on one end of the bus or the other end of the bus or different things like that. So you do have a few less things to consider as far as the response to bus faults compared to lines or some other types of equipment. So once we select our protection, generally what we're going to do is we're going to set that bus protection up to operate a lockout relay. And lockout relays are either physical switches that are electrically operated, or can be implemented logically within the relay logic as well. But those are designed so when the trip happens, it will both provide a tripping function for the appropriate breakers, so to clear all of the breakers on the bus. It may provide a breaker failure initiating signal, but it'll also block closing of the breakers. And that lockout acts as a latch that holds in the trip and block close until somebody actually goes to the substation to identify the cause of the problem, reset the lockout, and then allows the station to be re-energized. And that's really done to ensure that the problem has been resolved prior to trying to re-energize the bus. There are cases where you wouldn't use this, or that you may automatically try to re-energize a bus. But in general, for any kind of fault within the substation equipment, we're going to be using a lockout relay to ensure that the faulted equipment stays out of service until station crews have gone out to identify the cause of the problem and correct it. So similar to any protection system, we have some generic protection system objectives we will try to meet with our bus protection scheme. As I mentioned on the previous slide, reliability is very critical, where buses act as a connection point, really tying together large portions of the system. We really want to make sure that we're providing a highly reliable protection system that's both dependable and secure. Make sure that it's going to trip when there's a fault and we'll remove that quickly, and also make sure that it's not going to operate for faults outside of the protected zone, because obviously we don't want to be tripping off that large portion of the system if the fault is elsewhere, if it's on one of the adjacent lines or one of the other pieces of equipment that's connected to the bus. And that really comes down to our selectivity. We want to make sure we're only tripping this bus off when we absolutely have to. Speed is also a big factor in bus protection. Generally where you're getting a fault on a portion of the system that connects so many different lines and other equipment, oftentimes you'll have high fault currents at your buses, and clearing those in a timely manner is important for system stability, for equipment damage. It may be a scenario where you're really trying to maximize your operate speed and get it as fast as possible. Simplicity also comes into play here, as with any, ideally you're going to provide a bus protection scheme that's straightforward and easy to maintain. They can get a little more complex, where you may be looking at multiple sets of currents, and you need to make sure your current transformer connections and your tripping operation and things like that are all happening, because they do interface with more portions of the power system breakers and things like that. Trying to keep it as simple as possible is always a good approach. And then finally, economics. Generally, buses at being a critical component, we're seeing more and more utilities, even at lower voltages, justify some more advanced bus protection methods, based on the importance of all these other factors outweighing the economics of having to buy additional relaying and things like that for them. So we'll touch back on these in each of the schemes we'll be describing throughout the remainder of the presentation today. So the first type of bus protection scheme we're going to go over today is a time-coordinated protection. So this is a form of backup protection, in a way that you use either local or remote overreaching elements from adjacent protection systems to also operate for the bus. So generally, this is a non-dedicated bus protection, so we wouldn't be installing a separate bus relay for protecting the bus. But instead, we'll be relying on the fact that our adjacent line relaying or other local protection of the station, in addition to protecting the equipment that is designed to protect, will also see faults on the bus, because generally we're setting those with sensitivity plus some margin to make sure that they're overreaching the protected equipment, to make sure all of the protected equipment is covered. But we'll also look past the end of that, and we'll cover the bus as well. Now the limitation here is that this is a time delayed type of protection. So for instance, the distance elements shown here. Your step distance zone 2 elements would overreach and see faults on the bus, but those are going to be delayed, between a third and a half of a cycle, of a second maybe. Um, so that you're sacrificing the simplicity of and economics of not having another relay with the time delay that comes with applying remote protection. So generally, where we see time coordinated protection used is really in distribution systems. There you've got less critical clearing requirements. You may have less redundancy requirements, and the economics of adding dedicated bus protection, may not make as much sense. Though we are seeing utilities move to using dedicated bus relays for distribution buses. Uh, More often these days with some of the other changes going on in the system. So really, you're not often going to see the primary protection for a bus at a transmission level be this time coordinated protection. So really the advantages of it are that it's inexpensive. You don't have to buy a dedicated relay. You're using other relays within the system that just happen to see past that. Past the end of their zone and will detect a bus fault. The disadvantages are it's slow. You're using time coordination here, so you're going to have to slow down the protection to coordinate with other adjacent systems. It's got low selectivity, so you're going to trip off potentially a larger portion of your system than you have to, and you have to coordinate that with other systems. It's a scheme that can be applied, but isn't maybe the best protection option from a protection engineer's perspective. So I've got a couple examples here of how time coordinator protection would work. The first one is a high side bus fault. So if we get a fault on the high side transformer bus here, as where I've got shown, we've got protection on the transmission system feeding that bus that will see that fault. So the distance elements here that I've got highlighted yellow will see a fault on the bus in their zone 2 step distance overreaching zone. And again, that would typically be delayed between 0.3 and 0.5 seconds. So they'll see the fault and they'll start timing. When the relays time out and their zone 2 timer expires, they'll operate to trip their local breaker, same way they would if they were tripping for a line fault. And you can see the 3 breakers here I've shown as opened up, and that would clear the bus fault and put the bus fault away. And that's, of course, assuming that the distribution system connected here is radial, so there's no fault sources or things feeding back up through the transformer. So this type of remote clearing has the advantage of being simple. We're using those existing relays, but one of the disadvantages is that you're going to potentially lose more customers. So obviously, for any bus fault here, you're losing the customers connected to the low side bus, the distribution bus. But in this case, with this type of scheme, you're also going to lose the transformers that are shown tapped off the tap transformer on the right hand line here. So any customers that are feeding that station would be lost due to this protection operation as well. One other disadvantage is that the local breakers at the station that actually had the fault are not tripped directly by this remote protection. So they may have to either be manually opened to isolate the system and bring the rest of those lines back online, or they may be automatically tripped off through other protection or logic methods that you could use to detect that the bus has been isolated and automatically open those breakers. You also have to consider in this type of scheme, if you're applying automatic reclosing for the lines, for the line breakers that have been tripped, and you're going to automatically try to close those back in to re-energize the system, you have to coordinate that with whatever actions you're taking when you have a bus fault. So you may need to coordinate that to make sure that the um, uh, breakers at the high side bus at the faulted station are clearing before that reclosing takes place, or else it'll close just potentially close right back into the fault. The other example we can see here, and this is a much more typical application for um, a time coordinated protection scheme, would be protecting the low side bus that connects all the distribution feeders to the low side of the transformer, protecting that with a local time overcurrent element. So if we have a fault on the bus here, and again, this is a radial distribution system, so we don't have any fault current coming up from the feeders back to this fault, hopefully. Uh, and we would rely on this time overcurrent element here, this 51 element, to see the fault, and that would use an inverse time characteristic or potentially a definite time characteristic. Um, and that would see the fault, it would time out, and it would clear the breaker to remove the source of fault current from the bus. Now, this would typically have potentially an even longer time delay associated with it because the overcurrent protection protecting the bus really can't discern the difference between a fault on the bus and a fault on one of the feeders. So that protection on the low side of the transformer has to be slowed down enough that it operates slower than the time overcurrent protection on each of the feeders. That way, if there is a fault on the feeder rather than the bus, uh, the time the, the time that it takes for the low side bus overcurrent protection to operate is slow enough that it allows the feeder to trip off. So, this could potentially take half a second to a second to clear this bus fault, even though it's a fault right in front of the relay. One possible way to improve the operate speed of a overcurrent based protection for this low side bus fault example would be to use what's called a zone interlock type protection scheme. And this uses a lot of the similar types of stuff. We're using overcurrent protection to protect our feeders. We've got overcurrent protection applied on the low side of the transformer that'll respond to a bus fault. And uh, the scheme, because all of these elements are locally at the same station, either wires outputs from the feeder relays or provides some other mechanism for providing a signal from the feeder relays to the transformer low side relay uh, to tell that protection if the feeder sees a fault or not. That way, if there's a fault on the feeder, it says, "Hey, there's a fault. I see a fault." Uh, and it'll send a blocking signal and prevent the overcurrent element on the transformer low side from operating for a feeder fault. Um, it would typically be able to operate not instantaneously, but it would have some time delay associated with allowing the blocking elements to assert and the signal to be received by that low side relay. And this type of scheme would really only be applied, in cases where you've got a fully radial distribution system. And it may be applied in parallel with other time over current protection that's not dependent on this blocking signal. Some of the advantages of this scheme is that it's inexpensive. You have the same relays that were present in the previous example. And that it's faster than time coordinated protection because you're providing that blocking signal. You may be able to have this scheme operate in a tenth of a second instead of half of a second to a second. Some of the main disadvantages are that it adds a lot of complexity to the scheme. You're having to wire signals from relay to relay. You're having to coordinate both the pickups and timing of that scheme and understand how that'll operate. And there's also some reliability issues with this type of scheme as we're seeing more distributed generation go on the system. So when we have a fault on the feeder or on the bus, if there's still some amount of current going through that feeder because you've got generation present that would backfeed onto a bus fault, it can potentially provide a blocking signal when you don't want one. When there's when it is a bus fault that you do want that protection scheme to operate for. So we see the scheme applied uh, uh, sometimes, but it's been maybe moved away from a little bit by many utilities because we are seeing a lot more generation in the distribution system. So to illustrate this scheme, we'll start with a feeder fault example. So this would be a fault that we would not want the zone interlock scheme to operate for. And we'll start with a feeder on this feeder fault on this rightmost feeder. The protection elements will assert, so both the transformer low side overcurrent element and the feeder overcurrent elements will assert as they will both see the fault and they'd be picked up. This would have roughly, if the fault's near the terminal of the feeder, near the station, it'd have roughly the same magnitude of fault current coming from the transformer as as what we would have for a bus fault. So both of those elements would assert, and your timer within your both elements would start. Because the feeder relay sees the fault, it knows that the fault is not on the bus because fault current, if it's a radial feeder, will only flow in the direction of the feeder. If there's a fault in the bus, there wouldn't be any fault magnitude present in the feeder relay. So it sends that blocking signal up to the low side overcurrent element, and that blocking signal prevents that 51 element from operating. Once the time overcurrent element in the feeder times out because its timing has expired, it'll operate to clear the feeder, and you will trip off just that one feeder rather than asserting everything for the whole bus. If we take a look at the same system with a bus fault example, we'll start off, we'll have a fault located on that distribution bus. The time overcurrent element will start timing on the transformer low side because it will assert to pick up the fault. And you can see that none of the feeder elements see the fault, so none of the overcurrent elements within those feeder protection assert. Because no blocking signal is sent from the feeders to the low side element, it'll allow the time overcurrent element in the transformer low side to time out after the short coordination delay we'd set to allow the blocks to apply. But in this case, they never came, so it can then trip the breaker or the lockout to operate all of the breakers at the bus. So typically that lockout would trip everything on the bus to clear the fault, even though just the transformer low side protection was required to be tripped with. That was the only source. Generally, we'll isolate the whole bus for a bus fault condition like that. So this scheme, you can see, you're able to speed up the protection by using those blocking signals to give the transformer low side relay a little bit more information about what's going on in the system. But obviously comes with a decent amount of complexity because you're having to work and interface between multiple relays to apply the scheme. So it's one of those trade-offs that it can be a good economical option for applying higher speed bus protection on radial distribution buses. but also comes with some limitations in the complexity and application considerations if you start having fault sources, generation sources, things like that, or looped distribution lines that may backfeed that fault through one of those feeders, because that could potentially apply an unnecessary block for a condition you would not want to block on. So some of the limitations that come with either a time coordinated bus protection scheme or a zone interlock type scheme can be overcome using a differential protection method. So differential protection basically operates on Kirchhoff's current law. Current into the bus has to equal current going out of the bus when you sum everything up, or else that means there's some other path for current to be flowing, and in which case would likely indicate that there's a fault on that piece of equipment. So we can accomplish this in a few different ways, but generally we're looking at a per phase differential zone. So we would sum up all of the A phase currents, and ideally they would sum up to 0. All the B phase currents and all the C phase currents, and we'd apply those as kind of 3 different protection zones, protecting each phase independently. And we can get that differential quantity in a few different ways as well. We can either wire CTs in parallel with each other, so electrically we're summing the currents generated from those current transformers. And we do this with CTs with similar ratios and connections, so we usually use the same turns ratio for the current transformers, as well as the same connection Y or delta, generally Y, for the summation, and that would be one method we could come up with that differential operate quantity. With modern relays, or many types of modern relays, we're able to do it digitally as well. So we would wire each set of CTs individually to a relay and allow the relay to use its signal processing and mathematic capabilities to digitally sum the measured quantities based on their magnitude and angle. And ideally, again, our differential quantity would sum up to 0 amps when we have a non-fault condition. So differential current really has a lot of advantage as an operate quantity for a relay. Mostly that during normal operation, when everything is summing up correctly, all the current going into the bus is summing up and equaling to the current going out of the bus. The operate quantity for the differential current is 0 amps. So, whether that current going through the bus is load current or during an external fault, you're going to get, and in an ideal case, you're going to get, 0 amps of differential current as your operate quantity. And that takes a big turn when you get a fault, because the currents going into the bus are all going to be additive. So basically your operate current is going to go from 0 amps in a non-fault state up to the full measured fault current for that location if you have an internal fault within the protected equipment. So if you have a fault on the bus, that you're going to swing from that 0 amp condition beforehand all the way to the full fault magnitude is what you'd measure in that operate quantity. So obviously this has a really big advantage for us as protection engineers, because anytime we can very clearly differentiate between a non-fault and a fault condition helps us meet our protection objectives. One of the challenges that comes with it is it can be sensitive to CT accuracy issues. So even if on the primary side of your equipment all the currents are flowing through the bus and everything's summing to 0, if you have different accuracies on your CTs, or you've got underrated CTs, or CTs that may have poor performance for that case, you can start to induce errors in there, and your measured operate quantity, the differential current for an external fault or even during load, might not sum up to exactly zero. So you've got to do some analysis and understand the performance of your measurement devices, accuracy of your relays, your ratings of your current transformers, things like that, to make sure that that's accounted for in your settings. In some schemes, such as the one where you're wiring CTs together in a summation circuit, you also need to have dedicated CTs for that scheme, because you wouldn't necessarily be able to wire multiple relays onto one set of CTs as you can in many other applications when you're doing this, because you're looking for a very unique measurement quantity of the summation of all of those CTs. So that can also be a challenge that you got to understand when you're applying the bus protection, and how you're specifying your equipment and CTs and things like that to make sure you have the appropriate ratings and the appropriate quantities of CTs where you need them to apply the protection properly. So we can really look at a few different types of differential schemes. There's a whole bunch of different ones out there, but generally we can look at in kind of three different types. The first is a differentially connected overcurrent. It's a very basic scheme that just sums the CTs up and looks at the differential quantity and makes a decision solely based on that. The second one is a percent restrained differential scheme. So again, if you've got CT accuracy issues, or there's some other considerations that go into it, when you start having CT performance, just directly looking at that operate quantity could result in in you potentially making an incorrect decision. So percent restrained differential takes not only the operate quantity, but also looks at the overall magnitude of current flowing through the bus to determine what the pickup needs to be when that trip decision is made, how much differential current you need to see. And the last type is a high impedance differential scheme. So this operates on a completely different philosophy than the other current-based schemes, and that instead of just measuring the current, you're actually applying that current over a high impedance and taking a measurement of voltage over that impedance to make a trip decision. So we'll talk a little bit about each of these schemes and some of the advantages and disadvantages of those in the coming slides. So the first and probably simplest of the differential bus protection schemes is a differentially connected overcurrent scheme. So this is a scheme shown off to the right here, where basically we're taking our CTs off of each element connected to the bus, and this could be lines, transformers, cap banks, basically any component that's connected to the bus that could have current flowing into it, we would need to measure. So we sum all of those, and this would generally, for a differentially connected overcurrent scheme, be the summation would happen through wiring your CT secondary circuits in parallel. So you'd have all phase A CTs wired in parallel with each other, and the output of that parallel combination would go to your overcurrent relay. Same for phase B, same for phase C. And the overcurrent relay is basically just measuring that differential current. So assuming everything's ideal during normal load or external faults, we've got 0 amps. When we have a bus fault, we jump from that 0 amps up to a higher quantity, which would be the full fault current that we'd expect to see for a fault at that location. So it has some advantages that it can be high speed. Typically, this can be applied as an instantaneous trip, though sometimes you do apply short time delay to that element, or even a inverse time characteristic. But generally, you can apply it instantaneously, because if you're seeing a high magnitude of differential current, it's very likely that you have a fault on the bus. So you don't need to necessarily coordinate that with other equipment, where it should only be operating for faults within the protected zone and won't respond to faults in the other parts of the system. So you can set a high speed and also has fairly high selectivity that you ideally know right where the fault is when the fault's on the bus, and you know you don't have a bus fault when the fault's external to the bus zone. So you don't have to worry about that coordination, and you make a trip decision based on that. Um, the disadvantage is you have reduced security on this scheme if you have any kind of CT measurement accuracy errors. So current transformers are rated in a way that they maintain generally within 10% of the primary quantity is the expected error on your typical relay and class CT. But that only covers up to a certain amount of uh, fault current and connected burden. If you start having currents that are too high or you've got too much of an impedance connected to the current transformer, or it's just underrated for the application, you'll start to see the output of the current transformer will be reduced. So if you have that, and let's say your current transformer starts to saturate, which is what we call it when it no longer is reliably replicating the primary currents on the secondary side. So if one of your transformers starts to saturate and starts to put less secondary current out and has a higher error, that's going to drive a differential current uh, being fed to that overcurrent element because one of your CTs is putting out less current than it should, so the others that are putting out the full amount of current as expected aren't going to sum to zero anymore. So that's the main disadvantage, and because of that disadvantage, we don't really see a lot of utilities using this as a new scheme. We interface with these occasionally on an existing substation, but generally we're not going to be applying new differentially connected overcurrent schemes. So one way to overcome some of the security concerns that come with CT accuracy issues associated with differentially connected overcurrent scheme is to provide a bit more of an advanced scheme called a percent restrained differential scheme. And this still operates on the same basic premise that you sum your currents together, whether it's through wiring or through uh, you know the relay algorithm, digitally summing those currents, and you operate on that differential operate current. But what it does is it also adds a restraint quantity to it. And what the restraint quantity does is basically looks at the overall magnitude of current seen by all of the inputs. And if you're in a higher current scenario for an external fault or for an internal fault, if overall it's measuring a large quantity of currents, it's going to require more differential current to make a trip decision than if it was in a very low current state. So for the case of let's say load current, where you would not expect to have any CT saturation, it would take a smaller amount of differential operate current to make a trip decision than it would for an external fault, where the CTs are more likely to saturate. At that point, that you're going to have to drive a lot more differential current to make that trip decision. So oftentimes in modern relays, the CT secondary circuits would be individually wired to a relay. So you take your Y-connected three-phase CTs and you'd wire those into a relay input, and you do that for each of your connected elements. And the relay can then digitally sum those together to make the operate current, but then can also calculate another quantity that's your restraint current that you compare to your operate current. And the trip decision is made when the ratio of operate current to restraint current hits a certain point that's a percentage value, which is what you'd use for your setting, which is why they call it the percent restraint differential element. So one of the restraint, there's multiple different ways you can calculate or measure that restraint quantity, but one of them I have shown here is basically, your operate current is the sum of all your currents, and that's summing up, considering both the magnitude and angle of each of those current measurements. And then your restraint quantity is the sum of just the magnitudes. So for an internal fault, those would roughly be the same quantity. But for an external fault, your differential current, even with some CT saturation, is going to be a fairly low quantity, and the restraint current is going to be a fairly high quantity. And that really secures that differential element against some of the effects of CT saturation. So the advantage of the scheme really is that the restraint current secures this element, and you still have to consider your CT saturation, but you're a lot less prone to misoperation for CT saturation. These types of relays also have the advantage, if you have one of the modern types of relays where you're wiring the CTs in individually rather than summing them externally, is you can also apply these for CTs with different ratios. So if you've got a 3000 to 5 amp CT on one breaker connected to the bus and a 2000 to 5 amp CT on another, you can still wire those both to the relay and use the settings within the relay to compensate for those. Because you've secured the element using the restraint quantity, you can also set the operate to be set very sensitively. So you can set the element to respond to a very low magnitude of differential current for certain conditions. So if you've got a bus with a relatively low fault current magnitude, this scheme can generally be used to provide the sensitivity you may need. And you also have a high selectivity. So, with this type of element, you've got a very clear understanding of where your fault is, and you're able to just trip off the bus and for bus faults, and you're able to restrain the element and prevent it from tripping for external faults. So because it's all contained in the currents, to find that zone of protection, you don't have to worry about coordinating this with other protection methods and other protection schemes for the adjacent equipment. The main disadvantage is its higher cost and complexity than some of the other schemes that we've talked about. So generally, you're going to have to be installing a dedicated bus relay. You're going to have to be doing some more advanced configuration to define how everything's connected up to it, and make sure that these equations are summing up to the right quantities. So there is some additional cost and complexity that comes with it, but generally we're seeing these used almost everywhere on transmission level buses, and are seeing them more and more on distribution level buses and subtransmission buses, as well as utilities are really seeing the benefit of providing higher speed clearing and some more advanced protection on subtransmission and distribution buses. So we can take a look at what kind of currents would we be expecting for operate and restraint quantities on this type of relay scheme during a bunch of different scenarios. So the first one we can take a look at is during normal operation. We've got load current flowing through the bus. What do these quantities look like? So in that case, this would be a case we would not want to trip, because you don't want to trip under load, and there's no problem with the bus at that point. So because the operate current is going to sum the currents directly, including both the magnitude and angle, the expectation is that current would be flowing in through some of your sources connected to the bus and out through others. So your operate quantity is going to sum to 0. the restraint quantity for the type of restraint calculation shown is going to sum the magnitudes of all those currents. So all of those currents into the bus and out of the bus are going to be additive. So generally, we'd expect to see 2 times the load current in restraint current for a load scenario. So on the operate characteristics to the right, which show the x-axis as your restraining current and the y-axis as your operate current, and then you've got a line in between it that is your setting of basically that percentage that you need operate current compared to restraint current to make an operate decision, to make a trip decision for this element. So that load current is going to basically plot right on that x-axis because you're going to have a low measurement of restraining current, but you're not going to have any operate current. So you're going to be in the portion below the curve, below the slope characteristic, where the element's going to restrain or not operate for that case. During an external fault, where you don't have any CT saturation, so your secondary quantities on your CTs are still reasonably representing the primary quantities, you're going to have something very similar. You're going to have basically no operate current, or very low operate current based on whatever errors you do have in your system. And the restraint current is going to be 2 times the fault current because, again, you're summing just the magnitudes. So you're going to have roughly twice what's flowing through the bus because you're going to be summing it when it comes in and summing it when it goes out. So again, that's going to plot right on that x-axis of the restraining current and fall well below the percent characteristic, the slope characteristic, and it'll fall into that restraining or no operate zone. So what's going to happen when you have some CT saturation in that same case? You've got an external fault, so it's a fault you don't want to operate for, and you're going to have some amount of error. So that error current is going to show up in your operate quantity. So you're no longer going to be at 0, but you're probably not going to be at a very large quantity. At worst case, you've got a CT that's fully saturated and you might be somewhere near the fault current. But your restraint current is going to be some magnitude higher than that. So you're going to have a higher restraint quantity than you do your measured fault current. So in any of those cases, if your slope is set correctly, you're still going to be falling into that restraint region. You'll be up off that x-axis. You'll be plotting somewhere higher than that because you will have some measurable operating quantity. But ideally, you'll still be falling into the restraint region. During an internal fault, your summations basically become the same. The current going into the fault is all going to sum up to the fault current. And your restraint current is also going to sum up to basically the magnitude of the fault current. So you're going to be plotting at basically 100% characteristic that your operate and restraint current are equal. And you'll plot above that slope line in the operate region of that element. So because of this characteristic, you're really able to set your element pretty sensitively and have it still maintain reliability and security during CT saturation events. So last type of scheme we're going to look at is called a high impedance differential scheme. The scheme uses externally some CTs to provide your differential current. And instead of just being connected over the relay impedance, which would generally be a very low impedance current input to the relay, it's going to be connected over an intentionally high stabilizing resistance that we have shown down here. And that's going to drive a voltage across the stabilizing resistance that's going to be monitored to make the trip decision. So generally, we're also having some stuff to further protect the circuits here. We might have an MOV included that would prevent high voltages from forming across that stabilizing impedance. We may short out the impedance once a trip decision is made using a contact from the lockout relay. And we may also provide a differentially connected overcurrent element, so another low impedance type element um, in series with the high impedance element and the voltage element that can be used for other things, basically to, as part of a breaker failure scheme, or in cases where, maybe you've taken the high impedance element out of service or it's otherwise disabled, you can use that overcurrent element. That's not a feature on all high impedance relays, but many of the modern type relays do include that overcurrent option. So this type of scheme has the advantages that it can be set with high sensitivity, it's got high selectivity, and it can operate high speed. So it's a scheme that's been around for a long time and is really was a first choice for high speed bus protection for a long time. Some of the disadvantages is that in order for the scheme to operate properly, you really have to have CTs with similar ratings, and they have to have matching ratios. So if you've got differences and you've got one breaker that has a 3000 to 5 amp CT and another that has a 2000 to 5 amp CT, you're not going to be able to use those current transformers for this application. And ideally, they would all be the exact same make and manufacturer and rating CTs, so they all have the same current transformer saturation and performance response. The CTs also have to be dedicated to this relay, so you're not able to use those CTs for other additional circuits if you wanted to wire a breaker failure or use that same set of CTs for some other function. You would not be able to do that in this type of application. So this scheme is monitoring a voltage over that high impedance element. And we can take a look at what that voltage looks like during certain scenarios to determine how we can make a setting selection that's going to operate reliably using this type of protection. So in the upper right here, we've got a circuit. Basically, it's the left-hand portion of the circuit is the equivalent of all of the CTs but one provided in parallel. And you can see we've got an ideal current source. We've got a nonlinear impedance that would be what we'd use to typically model the nonlinear response, the saturation performance of a CT. We've got RCT, which is the resistance of the CT windings themselves, and then we've got RL, which is the resistance of the cables that connect up between the CT set and the summation point, where we're summing all these CTs together. On the right-hand portion, it's the equivalent of one additional CT. So it's really to show the current would be flowing through that CT out onto your other sources. For the load current example here, or an external fault with no CT saturation, the current in the left-hand portion of the circuit is going to be the same as the current in the right-hand portion. So the secondary current's just going to flow from the CT equivalent A on the left through the CT wiring and the CT winding resistance, and then flow right over into CTB, and that will just go in a circle, and basically there'll be no current driven across the stabilizing resistance RS, which is that high impedance quantity. So if we measure the voltage across RS, we're going to, because we don't have any current going through it, the operate quantity there is going to be roughly zero, because there's really no current flowing to drop a voltage across that high impedance element. If we move to the right and consider an external fault with full saturation of the CT, so this is the worst case that the CT has fully saturated and one of the CTs on your from your summation point is putting out 0 amps of current. So even though it's seeing a primary quantity, it's saturated to the point it's not putting out any current at all, which is probably unrealistic. Generally, you're going to still be getting, even with CT saturation, you'll be getting some amount of current out of your CT, even if it is reduced based on the saturation performance. This is really your very worst case, that one of your CTs is fully saturated and is putting out 0 amps. So you can see we've removed the current source and nonlinear impedance of the CT and replaced it with a short there. So what happens in that case is you end up with a fault current loop around that CT that's fully saturated, and that fault current is going to drop over your CT lead resistance and the CT winding resistance. So you're going to end up with a measured voltage VR that's basically your CT winding and lead resistance times that fault current, and that'll be the voltage that you'll measure for an external fault with full saturation. So for that case, you are going to have a voltage applied over the high impedance element, but ideally it'll be relatively low. And then the lower figure here, we've got an internal fault case. So in that case, all of your CTs are summed together and they're all feeding the fault. So basically, the entire fault current in that case is going to be dropping over your stabilizing impedance, the high impedance element, and the voltage that's driven there is going to be really only limited by the saturation performance of the CTs. So if you look at the specifications for the CTs, and they generally include some performance curves, so you can look up and see, the maximum amount of voltage that those CTs can provide, and that will roughly be the voltage that you're going to be seeing over this high impedance element. Because it's a high impedance, it really drives the CTs into full saturation, and you're going to drive a limited voltage over that. So what we can do is we can use these three quantities, what we expect to see with load current or a fault with no CT saturation. We don't want it to operate for that. That's 0 volts, so that's easy. We can use that as a baseline. We'll also look at what's going to happen in our worst case saturation of a single CT, and that'll give a value. And then we're going to need to set it some amount above that, so we make sure that we don't operate for that worst case external fault CT saturation measurement. And then lastly, we'll need to look at what happens on an internal fault and make sure that we're able to set our voltage pickup below that voltage to make sure it does operate for the internal fault. So this scheme operates on a really different principle than our other current-based schemes that we've talked about, but can provide some really highly sensitive, high speed, and very secure protection. So it's a good choice, and it's still something we see regularly used by utilities, even though it's a scheme that's been around for several decades. So to wrap things up, bus faults require tripping of all sources connected to the bus. So we really, have to put a high focus on those protection objectives and specifically the reliability of that protection, as it's really critical. You don't want to be tripping buses off unnecessarily. There are several ways of protecting substation buses that each have their own advantages and disadvantages. So we talked about time coordinated protection, zone interlock schemes, a few different differential type methods, and they each have certain advantages and disadvantages that need to be weighed when a protection engineer is deciding what scheme is appropriate for a given application. And that's really going to be driven by the system performance requirements, so the reliability requirements and selectivity requirements and speed requirements, the types of current transformers that you have available for your application, and then really the cost and complexity. So obviously, if it's a non-critical part of the system, and some of these other factors don't come in, maybe you can provide a less robust protection package for your bus. Though we are seeing utilities move towards providing more advanced bus protection even on lower voltage buses due to some of the performance and reliability considerations that are coming into play. And really, when you're applying bus protection, you really have to have a good understanding of your CT connections, the ratings, saturation performance, making sure you're connecting up the relays and the CTs with polarity in mind. And that's really all going to be very critical to application of bus protection, specifically with differential type schemes. So it's certainly something you'll see a lot of as a protection engineer, and it's something to gain some familiarity with. So I appreciate everybody listening in and following along on this presentation. So I've also included a few references here that I used in building the slide deck. These are some great papers and industry documents that can be used to learn more about bus protection, and I encourage everybody who's going to be applying one of these schemes to really leverage the wealth of information that's out there from various sources, because there's a lot of really great information that can help guide you to some of the more detailed and kind of nuanced considerations for these schemes. Well, thanks everybody, and I really appreciate everybody listening in on the content today, and hopefully it sets everybody up for a better understanding of bus protection and some of the considerations that go into it. There's certainly a lot more content and things you can dig into to learn a lot more on the subject, and I hope you do. All right, thanks a lot.